Hello, everyone. Welcome to this week's graduate SFI seminar. And today is my great pleasure to introduce our speaker today, Andreea Stoica. Andreea Stoica is a PhD candidate at Columbia University. Her work focuses on mathematical models, data analysis, and inequality in social networks, from recommendation algorithms to the way information spreads in networks, and is particularly interested in studying the effects of algorithms on people's sense of privacy, community, and access to information and opportunities. She strives to integrate tools from mathematical models, from graph theory to opinion dynamics, with sociology to gain a deeper understanding of the ethics and implication of technology in our everyday lives. And she grew up in Bucharest, Romania, and moved to the US for college, where she graduated from Princeton in 2016, and with a bachelor's degree in mathematics. And since 2019, she has been co-organizing the mechanism design for social goods initiative. And just a few instructions for the audience in the room. So we have a camera plus the mic in front of the room. So if you want to ask questions, you can just speak freely, and I will be able to hear all of you. So cool. And without further ado, Anna, the floor is yours.
Great. Thank you, Sam. And thank you, everyone, for inviting me. It's really nice to get to see you all. And it's the first hybrid event that I've been a part of. So this is really cool. And seeing how the mic works was really cool earlier. I'm really excited to talk to you about my research. Please feel free to interrupt, either just ask a question or use the chat. Most of my research relates to a couple of projects that I wanted to talk about related to social networks and inequality. But I was also hoping but I can go in as much detail as you'd like to hear about it. And I can also chat about an organization that I've been a part of that relates to how, like, the research that I do as well. So let me share the screen right now. Stop me if you cannot see it. All right, so I'm at Columbia, as Sam said. I work there with my advisor, Augustine Chantra, and our research relates to diversity, inequality, and social networks. The main question that we're posing is basically, what is the role of social networks in creating or perpetuating inequality? And that relates to a couple of projects that I will mention today, to the social influence maximization problem, which relates to how do you diffuse a message into a network in an effective way, and to recommendation algorithms that leverage your network information. So the first point that I want to bring is, oftentimes we think about the pipeline of having a graph which has some sort of like biases or inequalities in it, depending on how people are connected to each other. There's an algorithm that works on this graph, and there's some outcome that may or may not be biased that we're trying to evaluate and sometimes to fix. And the very question of what does it mean for an outcome to be biased depends on what application you're looking at. So, for example, if you're looking at trying to diffuse an information into a social network relying on people's connection, you might look at a pattern of when people do not hear that information at an individual or at a group level as well. Similarly, if you think about the recommendation algorithm where you recommend people to connect to each other, you may think of like people who do not receive those recommendations or for whom those recommendations are just not as good. So with that in mind, these definitions of what does it mean to be biased or not will differ. And I wanted to delve more deeply into one of them, mostly related to the social influence maximization problem. This problem relates mostly to how do you diffuse a message into a network. So it relates to like the news that you read online that propagates through your friends or through just people you know, through the technologies or products that you hear about. It also relates to like running marketing promotions and seeing what products you hear about in advertising, and also in public health issues. For example, when you have a government trying to relay a healthcare campaign. And these last two are require very different algorithmic design, because the first one relates to like targeting a small group of people for whom this information is relevant, and you want a small and targeted campaign. And this is not the kind of application that we're looking at today. We're looking more at like an application that, for example, could relate to public health issues in which you need to run a really large campaign to maximize the number of people who hear this message and to like diffuse it as widely as possible. Of course, public health issues are not the only application, and we see a lot of work that relates to this as well. So the spread of COVID-19 is of course one of them, but there's related research, for example, in trying to understand how microfinancing loans can be adopted by people in need. This is an empirical study done on the ground in India, in trying to understand how information diffuses from one person to another in communities, and what kind of metrics can we use to understand the diffusion process, as well as trying to understand, for example, how would we raise awareness about things like HIV among the homeless youth if you have to rely on the community information, which provides a lot of leverage in actually diffusing a message properly. So these are the different, these are related works and that relate to different applications. And in this work, we'll start by thinking about this, that information, access to this information is actually like access to an opportunity in healthcare, and therefore there's a need to make sure that this is diffused in a way that doesn't leave groups or people out of the loop in a way that's just unfair. So to go over the main, how do we formulate this problem? This is a problem in which you have a network and you have some diffusion model in which you rely on people to diffuse a message. So if someone hears a message, then they're gonna relate to their friends with a probability P, and who relate to their friends with a probability P, and so on, in a process that cascades. And the point is that you can choose a set of early adopters who are the first people to whom you give this message, and you rely on them to create this cascade. And at the very end of this process, you end up with a set of people who have heard this message and adopted it, and this is your outreach. So the point is, how do you choose these early adopters in an efficient way to maximize your outreach? This turned into like a simple formulation of an optimization problem, but this problem is really hard. Like, it's incomplete. People have shown different approximation algorithms to solve it. It's difficult because oftentimes you have a budget on this number of early adopters, and that's depending on your central planner. If you can choose everyone in your early adopter set, you basically don't need the diffusion process. You just gave the message to everyone, but that's usually unfeasible. And you have the budget to give it to a small number of people, and then you have to rely on them for this campaign to diffuse. And this can relate to diffusion, to budget that relate to actually giving flyers or diffusing email campaigns, or like things like that, in which you don't actually have access to every single person in your population. So to solve this, people have proposed different approximation algorithms, and they choose these early adopters in a strategic way. So you can choose by a measure of centrality, for example, degree or distance centrality. And the intuition is that you have people who are very popular, and therefore they have a higher chance of actually diffusing the message into more and more people as well, as opposed to choosing someone who's very, who is not really connected in the network, and then maybe they don't have a good chance at continuing this cascade. And you have different kinds of algorithms, like greedy, which is really great. It approximates the optimal solution really well, but it's very computationally costly, and you do need like full network information for it in order to do it in a greedy manner. So the question is, here we have this problem more or less figured out for when you have this optimization set up. And then the recent questions that came up is, what happens when you have different groups that are connected differently into the network? And these different groups, I'm portraying them here by red and blue. They can represent gender, race, different demographics, interest groups, and so on, for which people are connected differently with each other. And there's recent research that shows that, well, given these different groups, there's a bias in centrality measures and the social structure itself that can get reproduced from the early adopters up onto the outreach, and you may end up with large groups of people or communities who are just like left out of this information loop. That may matter in cases where, you know, for example, for like vaccine uptake or healthcare information, you want to make sure you target communities in a fair way, especially given, like in New York City, for example, groups are quite segregated still geographically. Sorry about the noise. I hope you can hear me well. And you want to make sure that this is not getting reproduced in the way that you give information to people in general. So great, if we're thinking about groups, then we get to basically a new optimization problem. So that what that happens is that if you think about these groups that are red or blue and they can basically represent any like demographic or interest group, you can set up a parity constraint in this optimization problem to ensure that your outreach population is reflective of the general population. So what the people you see in the outreach are basically proportional to everyone you see in the general population. And the issues with that is that people have noted there's like a fairness efficiency trade-off. And what I mean by that is the following. If you set up this problem without any constraint, as we just did before, you may end up with a great outreach, a large number of people who have heard this information, but maybe you're leaving one group out of the loop for this. However, if you are setting up this parity constraint, you may be more fair in the different groups that you are reaching, but you may reach overall fewer people. So that is the fairness efficiency trade-off that people have observed in this. And this is the subject of the study in which we're trying to figure out, well, what can we do about this? Is this reasonable to tackle or not? Are there any questions so far? And please interrupt if you can't hear me well, or if there's too much noise, do let me know and I'll adapt to that.
How does this handle when there's multiple potentially overlapping characteristics that you might want to control for? So like socioeconomic status?
Yeah, that's a great question. So these groups don't have to be completely disjoint. You can have people that are intersecting over these characteristics. And for that, you might think about like a hierarchical clustering and like think about how you can diffuse this message at every level of the hierarchy. That's not, we haven't formalized that problem in itself, but I think it's an interesting future direction to like look at. Does that answer the question?
Yeah, thank you.
All right, so what we're doing here is slightly different. It's basically saying, well, we're not going to look at greedy. Greedy is really expensive. You really need to know all the information. And we're going to look at centrality measures, for example, at number of connections. We're using this model of network growth to tap into the inactive communities that have not heard the message. And we show that actually you end up with, if you want to be more diverse, you can actually be more efficient. So you don't, there are cases where you don't get this trade-off, and we can analyze them closely. So this project is from last year with our collaborator Jesse Shinihan and my advisor Augustine Chantreau. The idea is that bias is a sign of inefficiency. And if you tap into the inactive communities in the early adopter set, you leverage their connections in order to get that into the outreach as well. So we're looking at two ways of targeting people not targeting, but choosing the early adopter set. In one way that's agnostic, you ignore labels and you assume that already takes into account the network structure. And one, and this is basically giving you the classic formulation of just like of this optimization problem. The other one is if you're actually aware of labels and you want to ensure the parity not at the level of the outreach, but at the level of your campaign. That may mean that you're choosing less connected people. We were looking at a set of heuristics that are doing that and comparing with a baseline that is just choosing people agnostically. So how would that look like? Basically, we end up with a new optimization problem. and this is at the level of the early adopters. This is still difficult to solve, but given a model of network growth, this is much easier to actually get some analytical conditions of how information spreads. And how this would look like on an actual algorithm or heuristic to say so is the following. Let's say you're looking at degree. And let's say you're sorting people by their degree, people who have very high degree, and you are going to choose a set of them based on your budget. So you're choosing some number of them of degree above a certain threshold K. And we know that the degree heuristic actually works pretty well in practice. It's not as optimal as the greedy one, but in practice, it's pretty close in terms of performance. And we're comparing that with a seed set in which you keep the same budget, but you want the statistical parity at the level of early adopters. So you're going to choose more of the minority group, here is portrayed in red, and fewer of the majority here in blue. So you might end up choosing less connected people from the minority, but overall you keep the same budget of people. So this would ensure like a strict parity condition. And we can do something in the middle, which is a relaxed version of that, which we call diversity seeding, which is simply something in the middle between agnostic and parity. So you don't want a strict condition on statistical parity. You allow some level of wiggling around, which we will show that's actually helpful in practice as well. So given this, what we get is the following. The setup is that you start with this network, you have some partial information, for example, degree, you have to choose your early adopters, and you do it in the strategic way, being aware of their community, and you hope to get statistical parity or some version of it for the outreach as well. And the idea is that being aware of communities and understanding these dynamics of connection can lead to better results. The key point here is that people actually connect more with people who are similar to them. So the communities that you see are more clustered, or in sociological terms, they're more homophilic. And using the model that I'm going to describe is helpful to understand that. So the model that we're using to understand this is a bias preferential attachment model, which means the following. You have two groups, majority in blue and minority in red. And you have this rich get richer effect, which is basically the same as preferential attachment. You have nodes that come into the network and they connect to other nodes with a probability proportional to those nodes' degree. So nodes who already have very high degree are more likely to get more incoming connections, and that leads to like a very skewed degree distribution. And the last thing that you have is also homophily, which means that if you have different labels, if you're in different communities, red and blue, connection is accepted only with a certain probability, whereas if you're within the same community, you always connect, meaning that you get this like slight clustering effect. So this model is cool because you get something interesting in the degree distribution of the two communities. We know that generally this model has a very skewed degree distribution and follows a power law. It's helpful to see and to analyze online communities because they're often very like sparse and skewed, and they approximate a smaller pretty well. But when you have these two communities, you get an added interesting effect, which is the fact that each community actually has a power law distribution for their degree, and the two coefficients of that are different. And that difference is something you also see in different communities in online networks, and is the tool to get you an analytical condition for this diffusion process. So it's not only that on average people have different degree if they're in different communities, is that the degree distribution is actually different with different coefficients. So what we get with that in mind is that, well, if you look at these two algorithms, diversity and parity, you're actually going to get to fair outreach for the same budget. And that is intuitive because you have this network in which you have groups that are more connected with each other. You're choosing more of the minority in the early adopters, so you see that more in the outreach as well. So it's, in that way, this makes sense. The one that's less intuitive, it's that actually both of these can outperform agnostic seeding in outreach. You can get more people overall with certain conditions, and when you have a large enough campaign. And this campaign large enough does not mean getting everyone into the early adopter set. You get an analytical condition, and I'm going to show you when exactly you get that on some simulated and real networks as well. So what happens in the end is that if you have too small of a campaign, you can't be fair and efficient at the same time. That's where agnostic seeding behaves the best. You get a small trade-off. This trade-off is actually not that big. And when you have a large campaign, that's where parity seeding outperforms agnostic, and you can be more fair and more efficient at the same time. And if you don't have such a big budget, if you have somewhere in the middle, which is often the case, that's where diversity seeding can also outperform agnostic, and that's where you can still not have a trade-off. And it's helpful in this way. I heard something. Are there any questions? All right, if not, I'll keep going. All right, so these are the three heuristics that I was just mentioning, right? The agnostic seeding, where you're just choosing based on degree, the diversity, which is a relaxed version of parity seeding, which has this like strict parity condition for the early adopters. So let me show you how this looks like. This is the interesting part. Oh, sorry, this is an extra slide, but a theoretical analysis for this diversity intervention. So what we do here is that we simulate a bunch of networks that are basic from this model that to show how these theoretical results actually look like. And these are more or less, the networks are more or less looking like the data. We also do this on data, and the simulations are trying to look like the data to get, well, how different is the theory and the practice actually looking like. So this is a set of simulated networks in which on the x-axis is the minority fraction. You have about like 53,000 nodes, which is about the size of our real data as well. Two communities, some homophily parameter that is trying to approximate the data. So the minority fraction means that for 0.1, you get 10% red nodes and 90% blue nodes. And as you move towards the right, you get to more and more equal networks. At 0.45, you get just 45% red nodes. And on the y-axis, you get the size of the campaign, the early adopter size. So that's just the size that I was mentioning earlier. And each of these points is basically a simulated network for these parameters in which we color each region by which algorithm outperforms agnostic or not. So when you have a small campaign, you see that agnostic performs better than diversity and better than parity. Diversity always performs better than parity because it's just a relaxed version of it. So it's always going to do better in terms of outreach. So the evaluation here is by the number of people in the outreach at the end of this campaign. And you see that when networks get a little bit, get more and more equal, at some point you transition into the blue side, in the blue region of the network, in which diversity actually outperforms agnostic. So you can be more fair and more efficient at the same time if you have enough early adopters, if your seed set is large enough. As you move towards more and more equal networks, you see that this boundary, this phase transition line is decreasing, meaning that when networks are more equal, it's easier to be more fair and more efficient at the same time, which makes sense. You don't need to, like the trade-offs are not only the trade-offs are pretty small, but it's just, you don't need that many seeds to actually make it more fair. So that's great in cases in which it tells you exactly what size of campaign do you need for each of these types of networks. At some point, when the seed set size increases enough for large campaigns, you transition into the purple region, which is where parity seeding also outperforms agnostic. So that means you can be strictly fair and more efficient at the same time. But you need way more nodes for that in your early adopter set than you would for diversity, for example. And the interesting part is that the phase transition is no longer monotonic. You see that at some point, when the two communities become more and more equal to each other, you would expect to see the same effect. It's easier to be fair and efficient, but you don't. You see the opposite effect. You see that it's harder. You need way more nodes to be more efficient, strictly and fair, more strictly fair and efficient at the same time. And that is because when you get enough of the minority nodes, they already have like a large enough degree that are going to be somehow represented in the early adopter set. They're not a completely untapped community. So then it becomes harder to actually like get the exact representation of them in the outreach. You already have them in the early adopter set. You're not tapping into a new community that hasn't been tapped in before. They're already kind of there because there's already enough of them. So that's where it becomes harder, and that's where being like mildly like not strictly fair, but like in a slightly relaxed way, it really pays off to make this more practical to implement. So what's interesting is that the data shows this as well, and the data is actually showing this in an even more exciting way. We get this data from the BLP, which is the network of computer scientists, and we create a graph of citations in which you have two communities, men and women. And you get a graph that basically is about the same size, 53,000 nodes, and we estimate the sum utility parameter for the simulated data from the real data as well. So let me show you how the real data looks like. Let's say we are choosing about 1,000 seats. Your early adopter set is 1,000. You start with those, and then you rely on them for the cascade. And you look at the end of how many people do you actually get in the outreach, given a probability of transition. And what you see is that, well, this is right. The total outreach decreases for parity and diversity, not by much. This is an average over many simulations. You get to see that it becomes more fair for both of them. But and what you see is that actually in this data set, the minority are the women, which are about 18%. So we're looking at basically this vertical line through our simulation. So we're about like here. And you do see that parity and diversity improve that. Parity seating is, of course, like makes it like strictly fair, but you get a small trade-off. You lose a few nodes in the outreach. It's really not a big trade-off, but it's there. So it shows that we are indeed in this orange region. What happens when you increase the number of seats in your early adopters is that, let's say we make them 5,000, you would expect you're still here, but actually the theory is conservative. And on the data, we actually already transitioned into the blue region, and diversity seating starts to perform better. It's not by a lot better, but given the fact that you chose nodes that have much lower degree in order to get this statistical parity, they not only compensate for that lower degree in the outreach, they actually outperform it if the nodes that actually had higher degree. So further on, if we choose more nodes, if you're like around 9,000 seeds, then we actually in practice already transitioned into this purple region where parity seating also outperformed agnostic, and we see this trend as we increase the number of seeds. So in a sense, the intuition behind that is that if you keep choosing popular nodes that are from the same community, they have overlapping spheres of influence. You're not gaining much. It makes way more sense to try to be more diverse because you're tapping into a new community that hasn't been tapped before, and that becomes more complex where you don't get like such a clear differentiation. When you have like too few nodes, then it's easy to do that when the minority is too small. But when the minority is actually like pretty well represented, this becomes a little bit more complex in terms of how can you be more fair and efficient at the same time. Let me stop here for a second. This is the end of this project, so I want to see if there's any questions or thoughts for this.
For this data set you use of like including like male and female candidates, what's the like the actual percentage of the female candidates in the data set?
Yes, it's 18%. So we are about, if you look at this from like left being like 10%, right being like 45% minority, we are about 18%. We're like here on this vertical line where the percentage of women is 18%. So 18% out of the like 53,000, that's like 5,000. Oh, sorry, no, divided by, yeah. by 5. That's like about like 8,000, 9,000, something like that. I think that we're getting the number of women.
Okay, I see.
So this simulation is done for like any number of the minority, but then the real data is it's at a particular point where we have exactly 18%, 18.6 or 5. Yeah.
So before going into the seeding part, did you try just like subsampling and oversampling for the minority majority data set?
Yeah, so exactly. The degree, the diversity heuristic and the parity one are basically subsampling and oversampling for each of these. So parity, both of them oversample for the minority and undersample for the majority. And the way it's done is that the parity one oversamples with a very particular strict ratio that you need to get of the minority nodes in the seed set. Whereas diversity allows a little bit of a wiggle room, like a small epsilon that we vary to see, like more or less gives you the same results.
Okay, yeah, that makes sense.
Great. So let me go on with, please let me know when I'm close to time, by the way. I wanted to mention a different result, which is related to why do we need these models and why they're interesting to tell us something about how people connect and how algorithms react to that. This is related to a project related to recommendations, also with our collaborator, Chris Reader, and my advisor. And in this one, we're looking at, we started by looking at a data set from Instagram. And this data from Instagram had about 500,000 nodes. The women were slightly in majority, but the men had higher degrees. It says nothing about Instagram or anything. It's just the way the data was collected by our lab. And we tried this data set on the influence maximization problem as well. And we got similar results with the PLP as well. But I'm only showing the other one. So what happened with this data is that we're coming back to seeing like, well, is an algorithm like biased or not with different communities? In this case, like we're looking again at women versus men and what can we do about it? And what we see is that we do get this degree imbalance between these two groups. And we see that actually when you count recommendations, like the number of edges that are created through recommendation is going to get worse. So for example, if on the left side you see people with degree at least 10, which are about, I think, 1% of the total population, you get to see that there are about like 52% men and 48% women. And then you try some recommendation algorithm that uses these connections. So for example, like that uses some friends of friends heuristic. And we tried a few of them and we got, this is an example for what we got for one of them was that you get, if you add those edges, newly created edges, you get 64% men and 36% women among people with degree at least 10. So it made this imbalance like higher as you add edges through recommendation. And the interesting part is that this data was collected like quite a few years ago back, I believe my collaborator collected it in 2013, if I'm not wrong. And at that point in time, Instagram didn't have this like automatic recommendation of like who to connect to. So the algorithms that we tried for recommendation are in a sense like we can understand their effect because we assume that the network is created organically without recommendation. So we're looking at these two models, right? We looked at, in the previous project, we looked at this like organic growth model where like nodes come in and they connect with preferential attachment and homophily and have two communities. And we saw how that model looks like. And then in this one, we see that, well, what happens if you actually like add a recommendation? And the recommendation here in the model, we look at the random walk of length 2. And we get in some interesting results on that. We got that, if you remember, that the two communities are different with different coefficients in the degree distribution power law. In the if you add this random walk of length 2, you also get two different coefficients with two different power laws, but we're able to show that they actually grow further apart from each other. And that's where you see that the friends of friends can actually like not only polarize people more, but that polarization leads to this degree distribution, like growing further apart from each other. So that's another place where like inequality comes from. And you might think about that. That's where an algorithmic, a simple algorithmic tool is not, it's kind of leveraging this process of the two communities being homophilic, and it's making it worse for one of them in this case. So that brings up the question of like, you have this fairness metrics and where do you intervene, right? Like in the previous project, we looked at, you have this, it is a social influence problem, you have some inequality, and we can intervene with statistical parity at the level of the algorithm, and that works well. There are several related works with recommendation of like where exactly you can intervene. Should you pre-process data or should you do something else? And the very definition of how you do this really, really matters. In our case, you know, statistical parity is not necessarily the only thing you want to understand recommendation inequality, because you want to understand the exact degree distribution changes, and you might need other metrics for that, right? In other scenarios, I'm just going to briefly mention a couple of more recent projects that in which, you know, maybe statistical parity is not enough. So we looked at how if you want to group people in order to, for example, create school districts or to create like good voting districts, statistical parity doesn't really work that well, because on the one hand, you may end up with some gerrymandering issues like cracking a population into different districts and therefore not having them represented in their voice. Or it might just be like incredibly difficult to attain a proportionality metric. And that's where you like, we looked at other metrics, for example, at margin of victory from computational social science to understand social choice, to understand and to mitigate some of the inequality when your algorithm is about like grouping people rather than offering recommendation or diffusing information. So that's I know we're like close on time, so I don't want to mention too much about this, but this question of like, how do you define like what's good or not really depends on these applications, and you might end up with different definitions that some of them come from like statistical measures or notions of machine learning, or some of them can come from other fields in which they become more relevant. We have a survey of this from last year with my collaborators, that we're trying to understand where exactly these definitions create gaps and where they can fill up the gaps between fields like machine learning and mechanism design. And from machine learning, often this notion of statistical parity came from the fairness in machine learning literature, as well as like individual fairness. Whereas in mechanism design, you have more this like social welfare, how much does everyone get out of a system? You do get notions more related to the computational social choice one that I mentioned as well. And there's a lot of tensions between these two definitions, and it's really important to adapt them to the particular application that you have. In recent works, we see that there's a tension between like being fair and welfare, because the utility that you might get out of for a particular person might be different than the notion of efficiency that you have set up to be between different groups. There might be like longer term effects of fairness as well, depending on how people like react to the algorithm that you have put in place. So there's more recent work related to how people may have strategy and react to an algorithm as well. That relates to this project on recommendation, because you may say, sorry about the noise. You may ask, what do we do with the fact that the recommendation polarizes people a little bit more? Like one intervention on point is to say, oh, just recommend people more opposite content to each other, or more like opposite groups to connect to, and then that's going to fix it. And there's a study that's, it's not that recent, it's from a few years ago when the red feed, blue feed came into existence to see how polarized our Facebook feeds were. And they said, well, just recommend people opposite content. And what that showed up is that, well, people don't like that. People actually like got to be even more polarized if you don't fulfill their preferences in terms of recommendations as well. And if you try to kind of force this, like, for example, a parity condition on them to do. So it's not really clear what you do. You have to take this into account, and we can't like we can't really stop at like one statistical definition as an interventional point. And of course, all of the ones that I've mentioned before from machine learning really help us in understanding this like group level diagnosis, which is super helpful for the projects that I've mentioned before, and to think about like different definitions. So I just want to mention that to bring more context and to connect these projects. But I think this is mostly what I have. If there's time, I'm happy to talk more about one organization in which I've been a part of. It's Mechanism Design for Social Good. And it's very junior led. There's a lot of students in it. We don't only do mechanism design. We work on a variety of topics related to inequality, machine learning, and mechanism design, and others. And it's been really, the previous project that I mentioned stemmed from this organization in one of our working groups in which I work with other student colleagues. It's all online, so it happens with people all over the world. So we're trying to like tackle all these issues that relate to what are like groups that are disadvantaged and how can we think about computational tools to help them in different applications. So all of our groups are like particularly depending on like what application you care more about. So that's one place where I learned a lot about how these different fields interact with each other. And I'm going to stop there, but I'm happy to talk more about this if you're interested in joining. And I think we'll stop there and take some questions.
Great. Thank you, Anna. Okay, yeah, I think so. Yeah, so here's our Q&A session. So people in the room can just speak freely, and I will hear you. And for people on Zoom, you can mute yourself, or you can type the questions on the chat. So I have a question for Anna. So in all these seeding, different seeding methods, like the parity seeding and diversity seeding, so you showed examples of the performance on just like two separate two populations, one majority and one minority. But what about like what about like a population with like a more different population, for example, like for example, the differences are not like are not like 1 to 0, or rather it's like an analogous difference.
So let me repeat to see if I understood that. Do you mean the difference in outreach between these two groups, if that's average? Was that a question?
For example, so it's like so the difference is not like maybe like the difference between the populations are like not so different. Like for example, like a male or female, or more like so it's more like yeah, continuous distribution.
Oh, I see. So, you mean if each of these groups is not like discretely different from each other?
Yeah.
Yeah. I mean, yeah. I think that's interesting. I think what happens is that the key point of that. Am I still sharing? No, I'm not sharing. Here is if you do have the same distribution in the degree distribution, you actually end up with the same. So here, if you have the same distribution between groups that are, it could be 2 groups, it could be like 5 groups, but this distribution is basically what's telling you if there's a difference or not. Whenever there's a gap between this, that's where you get to see that if you sample within this distribution, you sample of a variety of people with different degrees, then you're not going to see an inequality. You're going to see on average the same influence between people. But that's when, like, if you do have a gap between them, like sampling on average is going to get you this difference. between these groups. So it really depends on whether these distributions are actually different with different coefficients or not. That's like the core of like, why do you get inequality in information diffusion, and respectively, why does it get worse in recommendation? Like, for example, let me see if I have that example here, because that's a telling one. So this one is, let's say you have this recommendation, a model and the organic growth, right? So if you have a majority that has some degree advantage and homophily, you get this like difference and like this expansion in the degree distribution. However, if you get the other way around, that the minority has a degree advantage and some homophily, you get that the recommendation is going to have the same effect, is going to increase that difference, but in the opposite way. And what creates this difference between these two distributions of degree is simply, it's necessary and sufficient to have those three factors of our model, which are exactly like having two communities, preferential attachment, and homophily. If you don't have homophily, for example, you get the same degree distribution. Preferential attachment would lead you to a degree distribution with exactly the same distribution. If you don't have two communities, the exact same. If you don't have preferential attachment, you don't get this skewed degree distribution. You might get, like, depending on what you get, you might get an exponential one or something else, but it's not going to be different. It's going to be most likely the same. And that's where you don't get inequality. And that's where the root cause is basically like these three elements, when they interact with each other, they create this different distribution, and that has repercussions on an algorithm that you put up on the network. And then there's a question like, is that something realistic, these three elements? That's where the data comes in and says like, well, it kind of looks like those three elements are present, and the model can tell us why they're important. Does that answer the question?
Yeah, I'm sorry. I'm just pretty new to this topic. Pretty new to this topic, so not really familiar with some of the definitions.
No, these are really great questions, and so please keep asking. Yeah.
I have another question. So how do you handle noise in the initial labels? Say, like we have a set of minority and majority, but say some majority labels are misclassified as minority and vice versa. So in that case, like, does this algorithm handle that noise? Is it robust enough, or do we need to make some changes in the algorithm so that that noise is accounted for?
That's a good question. Yeah. So you might need some changes in order to make sure we don't have like robustness theoretical results for this particular one. What we did is to try in all of our simulations, like these are randomized over and averaged over, I believe it's about 1,000 simulations for each, if I remember correctly. So you do get like an average response, but if you do get some misclassification, it also really depends on how strictly fair you want to be. So if your level of strict, like how fair you want to be in terms of statistical parity can vary a little bit, and you can like you can correlate that with how much noise you have to make sure you're actually like gonna have some improvement. Like for example, here. So if you start with this and then you actually like, these are actually blue and you misclassify them and you're adding more blue, like that's gonna like mess it up. But depending on how you choose your thresholds, and that might account for the noise. So I think there's an interesting interaction between like how much freedom you have in choosing this and how much noise you have, and correlating that would give you a level of robustness.
So one thing I was wondering was, with a lot of the stuff, you can look at the like data from an actual graph and validate that. But when you are proposing like interventions with how you recommend stuff, or looking at how often somebody actually talks to their network about disseminating information. How do you validate your assumptions there match like real data when it's presumably difficult to like go and do some intervention in the recommender system of Instagram?
Yeah, that's a good question. Like, for example, we tried collecting data again after a few years from Instagram. It became really hard to collect it anymore. So we don't really have data with recommendation in place. What we do is like, we do see some experiments of like how people take up recommendations. So there's a question of like, do people actually take the recommendation you give them or not? So then you can model that with some probability of take up that you can estimate from field experiments. For the other project, you have the exact same question, like you want to diffuse a message. Do people actually take up the message the way that you want to diffuse it? Like, is this like model of cascading actually like good? You want to see if people actually like do spread it like that. Of course, it's not as homogeneous. It's never going to be homogeneous as like a model like this, but these models are inspired from like actual field experiments of how people do like share messages with each other. And in estimating those parameters are basically ones that we do see in real life. For example, like this, it's not this one, it's the one field experiment that does that, and it's interesting, is this one. So they actually try to measure like what metrics in the network are important for diffusing message, like with what probability do people actually diffuse message to their friends, and so on. So then the experiments we do with that we end up with like the real data here. We didn't try just this, we tried like a bunch of parameters that are within the values of what we see from such experiments. So the related paper that there's a bunch of related paper, but there's the one that I mentioned, and there's others that try to estimate that. We don't have an actual field experiment of diffusing a message to a set of like DBLP people or Instagram people. That would be really great to do. I would love to do that, but we don't have that.
Yeah, it's just too logistically challenging with like how Instagram stuff works.
Yeah, definitely. So it's a bit unclear, like if Instagram wants to diffuse a message themselves, is this how they're gonna do it? And like how much do people actually take up of that? I would assume that there's a lot of like diffusion of messages that are more related to like targeted campaigns. Like the ads that I see on Instagram are honestly like always on point, but I don't see like, you don't see like large campaigns run that much on Instagram. Like you do see some sponsored contract from like, for example, a city of New York, like had sponsored content on all sorts of social media for vaccine distribution, healthcare information. So you do see like, you do need these online communities to distribute messages. Like I could see like, there's a lot of like listservs from computer science that people use for like jobs and stuff like that. But I would love to see an actual experiment with it. Yeah.
Thank you.
I think if there are not so many questions, I think we still have 5 minutes left, and I want to talk more on the organization you work for. I think it's a mechanism design for goods.
I would love to. Yeah, definitely. Let me share screen again. Here. Right. So in this organization, I got to be a part of this a couple of years ago and to co-organize it with my colleagues. And right now it grew into like a much bigger organization. Oops. The pillars of this is basically the working groups that I had mentioned, in which we're like in each of them, there's like 30 to 40 people who meet online every couple of weeks and work together on projects related to all sorts of different topics. So for example, like our goal is to have this like pipeline between like research and policy and practice. And there are projects that lie all around this. One of the groups that I was in the bias and discrimination group, came up with this paper that I was just telling you about on different definitions. That's more like a pure theoretical research. And there's like a bunch of other works that lie in between these from my colleagues that stems from this working group. So it's been a really nice way to meet people working on completely different topics like economics and operations research and so on, who tackle these problems and to learn from them. And we hope this is a space where like this kind of research can have a place in itself as well. So we had a conference just a couple of weeks ago where this work was showcased together with not only work from the organization, work from everywhere else. So it's something you can join and you can see like what level of engagement you'd like to be in, but it's a place where like a lot of the research that I'm interested in takes place, and working with people who work on slightly different fields to learn from that. So again, I'm happy to talk a little bit more about it, but this is like the main idea of it. So you can always email me about it, and I can chat more to you about this this organization or about my research in general too.
I have a question. I wonder if this project is open source.
For the social influence one?
Yes.
We can make available the code. The data is available, both the PLP, and you can. If you email me, I'll share the data for Instagram as well. It's not, the code is not up on our website just yet, but we're open to sharing it, of course.
Okay, thank you.
Yeah, I can share Anna's email afterwards. Great. Cool. Yeah, so I think we are at the end of our seminar today, and thanks everyone for attending. And thank you, Anna, for giving us interesting talk. And for me, it's pretty interesting. Yeah, it's interesting to see that the recommendation system starts out with good ideas, but it inevitably leads to a huge gap in the population. Yeah, thank you. Yeah, thank you for today.
Okay. Thank you for inviting me. It was really great questions. And please email me if you have any other thoughts, questions, you want the data, anything else.
Good. Thank you. Yeah. Hope you have a good day.
Thank you. You too.